Why was the statistician disappointed with her new jeans? She complained that although the model looked good, that didn't translate into a goodness of fit. I actually made that one up myself. All right, so we are talking about goodness of fit, and we're actually comparing counts. So we're going to determine whether the distribution of counts fits the model that we are trying to use. Okay, we're going to look at the difference between observed and expected, and which is also known as the residual. For this, we're going to calculate something called chi-square. What we do, just like we were doing before with standard deviation, is you go observed minus expected, and you square it. But the slight difference is you divide by the relative size here, all right? Divide by the expected value to get the relative size. So this is a little different that we're doing right here. So this value is called chi-square, and it has a family of distributions like the t-distribution. And like the t-distribution, degrees of freedom matter. So it's calculated where degrees of freedom is n minus 1, but instead of n being the sample size, it's the number of categories. So let's take a look at a few chi-square distributions here. And this is off of GeoGebra. Here I have a chi-squared of 20, which seems huge. And you can see that the probability for this model is fine because it has 40 degrees of freedom. But as I lower the degrees of freedom, the curve changes a lot. I mean, it's not like t-distribution. Yeah, that one has fatter tails. This one is really changing. And you'll notice that it only goes to the right. So the bigger the degrees of freedom, the bigger chi-squared is without being unusual. Why does that make sense? All right. Well, that makes sense because if we have more terms and all we're doing is adding the relative sizes, we get a bigger number when we get chi-squared. So the more terms we have, or the more counts, the more categories we have, the bigger degrees of freedom. Okay? So unlike z or t, just saying, oh, my chi-squared is this, that doesn't indicate any probability. And you'll notice this test only goes in one direction. There is no left side here. It's only to the right, okay? So if you're calculating this with your calculator, which you can, second distribution chi-squared, it's always, your chi-squared is always the left value, and you want to use a really large value like 1,000, and then you still have to put in your degrees of freedom. But the good news is your calculator will actually do this pretty automatically, especially since you need counts anyways. So what are some assumptions and conditions that you have to meet? Well, it has to meet the counted data condition. The data must be counts, all right? For categories of a categorical variable. It's not like measurements, but counts, all right? The counted individuals should be independent from each other to meet the randomization condition. If they tell you that it's representative, that also works. They have one extra new rule we haven't had before. It's similar. Remember, n times p is greater than 10? Well, for this one, we need expected counts of at least 5 in each cell. All right, so if you don't have 5, we haven't met all of our conditions. Now, some rules of thumb. When you're doing this in your calculator, the observed counts must be integers. If you get a proportion, you need to convert it to counts. And if it's observed, it needs to be an integer. Now, expected counts don't need to be an integer. But if you get a proportion, you also need to convert that to counts. And be careful, the conclusion must be about the alternative hypothesis, not about the null. And remember, never say is true or proves in your conclusion. So let's go ahead and look at an example. This is from an article in Bronx, Hitting Home Runs is a Breeze. And they classified 87 home runs hit at the new Yankee Stadium according to the direction the ball was hit. Now, they said assume the sample is representative of home runs at Yankee Stadium. Is there convincing evidence that the proportion of home runs hit is not the same for all directions? So our null hypothesis is that the proportions are the same in all directions. And sometimes these are easier to write the null in words than it is with an equation or equations. Our alternative hypothesis is that at least one proportion is different. So you want to state your null and your alternative. Now, here in this chapter, we're actually going to be looking at 3 different tests. So once you do that, you need to tell them which test you're going to run. So far today, we're just talking about the goodness of fit test. So you're going to do the chi-square test for goodness of fit. There are 3 chi-square tests. All right, now we need to look at the model. Remember, expected counts is total counts divided by 5. So since each direction should be the same. And so you can write down your expected counts in your table. If you do not write down the expected count somewhere, you are not showing that that condition is met. So again, the conditions, observed data is counts, which it is. They told us the sample's representative, and all expected counts are above 5. So you can see that they are. All right, so all our conditions are met. Now let's start with the calculations. All right, we need degrees of freedom. There are 5 categories, minus 1, that gives us 4. For chi-squared, basically, that's going to be 18. You take your observed minus your expected squared and divide by your expected, and you add them all up. By the way, when you are doing this, it's strongly recommended that you write this down. You are allowed to write down this ... okay? You're going to use a chi-squared goodness of fit test. So even if you're doing this on your calculator, and you accidentally have, say, a wrong data point entered, but this all looks good here, it will be considered a minor error. So please, please, please write this down. I will ding you if you don't write that down. Okay, and here's the p-value, but how did we get that? So I could take this chi-squared after I actually calculate it by hand and look it up on the table. Remember, my degrees of freedom is 4. Or what I can do is go ahead and use the goodness of fit test. So here I have a list of all my observed counts, and I entered my list of expected counts. Then I'm going to go ahead, once I've got my both lists entered, go ahead and hit stat and test. Scroll down, it's a pretty far down, chi-squared goodness of fit test. See how it has list 1 and list 2 for observed and expected degrees of freedom, and then I hit calculate, and there you can see there's my chi-squared value, which actually matches down here, and my p-value. I can also draw it, and I'm like, let me go ahead and draw it. I always like to draw. And the cool thing is you'll get to see what the distribution looks like for this degrees of freedom. Ignore that box and whisker plot. I forgot to turn it off. All right. So you can see here, the only problem with the drawing is it's going to really round down that probability. So it's better to go ahead and leave up the actual calculation. So you can see here's the p-value. Remember, by the way, that this e to the minus 5 is times 10 to the minus 5. So that's just a shorthand. That e means the exponent on the 10 for scientific notation. Now, we'll talk about the CNTRB when we talk about our conclusion next, all right? So there's your chi-squared, and there's your p-value. So that's an incredibly low p-value. So we should reject the null hypothesis. There is convincing evidence that the number of home runs hit is not the same for all directions, all right? If I had had a p-value, then all I could say is there's not convincing evidence to say that they're not the same in all directions. See how I'm kind of wording it about the alternative hypothesis instead of the null. All right, now let me show you a cool thing about the contribution. So if you see this contribution right here, you can actually try to scroll through that. I find the easier thing to do is to go back into my list and hit edit. And if you go up, I was like, hey, where's my contribution list? It's not there, but you can pull it in. So I just go up to the list name, make it equal my contribution list, 7. All right. And if you hit enter, there are my contributions for each category. So I can actually see which one contributed the most to the chi-square. So the biggest contributor to chi-square in this example is right field, with a much higher than expected number of runs. Now, just because it has a big chi-square doesn't mean that it's higher. It just means it has a bigger contribution because it's further away from expected. The second biggest contribution is from left center, and that's because from center, I'm sorry, not left center, because you can see that one's off by 10, more than 10. So that one also has a big contribution. So what calculations should you be able to show? You can do this all on the calculator, but it's very doable by hand. So make sure you show the number of degrees of freedom for any table. So you should be able to show that by hand, which is not hard. The expected value of any cell. So you need to be able to figure out what the proportion is supposed to be there. The component of chi-squared for any cell. So that means the observed minus the expected squared divided by the expected. And the expression showing how the complete calculation would be done.